All right, welcome back. Good to be back in person. It was a total weird start to the term, huh? Um, and not a snow day. I don't know what happened there, but hopefully you kept up when the videos. This feels a little loud, yeah. Hopefully you kept up and the videos were helpful, and that that we can sort of hit the ground running here, right? So last time we did our first lecture on. Last time being online here, but we did our first lecture on dynamic programming. And the point I tried to make was that we have beautiful dynamics of pendula and things like this, and that a simple grid-based search algorithm can actually discover and understand those dynamics, those long-term dynamics. Check my connections, make sure that doesn't oscillate all lecture. Okay, so to do that, we did value iteration on a mesh, right? So sort of last time, yeah. On a grid-based approximation of our state space. So everything we did last time was we had discrete, discretized, if you will, states. We had discrete actions. Right, the discrete states were the nodes in the graph, and action was which arrow we took on the graph. And to do that, we were in discrete time too. But even in that coarse approximation, in some sense, of the dynamics, we found these algorithms that really understood the long-term behavior. They recovered the eyeball, right? So, but mechanics is continuous, and it's beautiful, right? Like, you remember our first thing I said was control is kind of the interplay between the plant and the controller, and you can write a lot of algorithms where you assume very little about the plant. Okay, but that's not this class. This class, we're going to open this up, and we're going to understand the dynamics and the mechanics and understand how to write optimization about that. And when we discretize, although the algorithms are very simple and clean, we throw out a lot of that structure, right? Maybe the simplest way to see that is that once I turn something into a graph problem, there's no notion of similarity between the nodes in the graph, right? You've just thrown that away. But if there's two nodes that are approximating very similar states in my state space, then you'd expect them to behave similarly, right? And if we just have lost that information. So powerful, but not where we ultimately want to be. We want to get back to the continuous versions of things when possible. Right, so roughly this lecture, we're going to think about basically taking the limit as, well, if I call this a delta x, so I'll say like the gap between my states, I'll call that delta x. This is just a jargon for intuition. We'll do it precisely. I want to roughly do this. I want to study the same dynamic programming algorithms we talked about last time, but in the limit where you've made an arbitrarily fine mesh, and something good should happen and does happen as the mesh points go to a complete, in the limit, it becomes beautiful again, and that structure pops back out. Okay, and so we want to understand that. So let's begin. One of the problems we worked through just our, sort of to introduce optimal control, we worked through the minimum time double integrator problem, right? Minimum time double integrator. So that was algebraically, that looked like this, where we had a limit on u, where you could hit the brakes full speed or accelerate full throttle. If you're a little, this is u, this is q, and you're trying to get to 0, right? And we said that the optimal control is bang bang. We said without proving. Oops, bang. I sort of just banked on. You have to just trust me that it can be proven. We'll work up the tools to prove it. It's more. You'll see at the end of the lecture today why it's actually still a little subtle to prove that. Right, and you've got some practice now with these state space diagrams. And remember, the way that this policy worked was there were a couple key trajectories where if I'm at a positive velocity and I'm hitting the brakes, then my velocity goes down like this. And there's many of those possible trajectories, but there's one magical one, which is the one where I started at some velocity that hitting the brakes gets me exactly to the origin. And similarly, on the other side, if I was going this way, I could hit the brakes in the other direction. Right? There's a set of those curves where the best thing to do in this whole part of state space is to be running this controller that's hitting the brakes as much as possible. That's my u equals -1 policy. And then the other side, if I'm anywhere over here, the best thing to be doing is my u equals +1 policy. And except for the point there where you're at the origin and you can command 0, everywhere else you're either +1 or -1. Okay, and so what we were doing last time was we were making these approximations of those dynamics by embedding a grid here, a graph, where you could have kind of the +1, the -1, the 0, if you will, discrete actions. And you can fill out a dense grid there. There's some details you have to address, which again, I've just banked that one as a future thing to address so far, where maybe it's, depending on your discretization, but it's very likely that taking action 1 for some fixed amount of time doesn't land exactly in the even grid point, so we're going to have to do some interpolation. Fine, that's a detail we'll address. Okay, but what I want to do today is take some limit where that grid gets arbitrarily fine and see something better come out the other side. So remember the conditions we wrote for that. That's pretty annoying, huh? I don't know which connection is loose, but it could be that one, huh? Well, if it's too bad, I'll just turn it off. I'll go like that until I need it. How about that? Just so you don't have some sort of flicker fusion effect. Okay, so the equations that we sort of used to reason about this, we worked up to coming up with the core equations. Maybe I'll put them over here. Talked about dynamic programming giving us an optimal cost to go. Right, so if my dynamics were described on that discrete thing as a function which says when I'm in some state and I take some action, I'm going to land in some other state. You'll see throughout I use S and A whenever I'm using discrete things, and X and U when I'm in continuous. There'll be a moment where that's hopefully super clear. Okay. And my loss function is the sum over time of states. Some additive cost here, which we called L. And the optimal cost to go was, we said that for all S, J star of S is the min over all A of this L of S A plus J star of F of SA. Right, that's kind of what we worked up to last time. And then similarly, we could pull out the controller, the optimal controller, optimal policy, which we called pi star for the optimal one. It's a function of the state you're in, and it's just almost identical to that, but it's the argmin over A instead of the min. That was a lot of writing for, so, you know, I can compute this quantity for all possible A's. The value that is obtained by the minimum value that is obtained, that's what you get for min. The A, which minimizes it, is the argmin, right? You guys know that notation. Okay, so this is just saying the A that was the minimum, that's the optimal action to take. Okay, and you should think about these two ways, right? First of all, we talked about this as a condition for optimality, right? First, if you just wanted to convince me that you found the optimal cost to go, or an optimal controller, you could produce a function j over the graph, and if I check these two conditions and they match, then that's just a condition for optimality. And the second thing, which is almost a coincidence, but a very convenient one, is that it also can be used as an algorithm. Basically, you can try to make that condition be true by having a numerical approximation of j, just a list of numbers on the graph, and evaluating the right-hand side, writing it into the left-hand side. That was the value iteration algorithm. Okay, but first and foremost, this was just the conditions to check. Any questions on that? At that level? Especially since we weren't in the same room when that came across the first time. Is that sort of notation okay? Yeah. J star is the optimal cost to go. Yep. Yep. So yes. So if you had an approximate cost to go, or just an arbitrary function like over the state, I wouldn't have written the star. Star means optimal. And then the other notation I sometimes will use is if I want to have an estimate of the optimal, I'll put a hat for estimate. So yeah, so this is optimal, and this is estimate. That particular equation is not an estimate, so I'm going to erase that again. But just those are the two superlatives that I sometimes put on my j's and my pi's. Yeah. Yes. Yeah. Yes. Because I finally started covering output feedback in class, and when you get to, it's not trivial. It's one of the hardest parts of writing a book that covers all these topics. Right. So I write like this, or x dot, let's say, and then I need y equals g of xu for the output in the general form, and when I got to that, I was like, shoot, now I have to pick a different, I have to go back and choose a different letter for my cost functions everywhere. Yeah. And L is good for loss. People in ML have been using L, wanted to be cool. Oh yeah, sorry. Mm-hmm. If you knew the optimal order, which is a tall order, yes, which is a tall, whatever, it's hard to do. It would be as hard as solving the optimal control problem, yes? But you're right. So people talk about things that are halfway between, doing a naive sweep, or they call it prioritized sweeping, where you take a guess and you try to do a clever update. In practice, even on CPUs, but certainly on GPUs, you can just make a big vector and do that in batch for pretty big problems. Awesome, yeah.
Also in the video, you said value iteration converges to the optimal value plus some constant.
That's right.
And so is it not unique? Like in principle, you don't need a unique
That's a great question. So if I were to just take these conditions and I were to add 10 to J, then that could still go through, right? Or add any constant to this, you'd still satisfy those conditions. So the conditions here are matched by any scalar or any constant addition to the function. However, I would say there is a true cost to go, which is the cost you actually accrue, which would be a combination of this with some boundary values, saying that, for instance, like you have 0 at 0 if that's the final thing, and that would be the true cost to go. So the value iteration converges to a cost to go plus the true cost to go plus a constant. Yeah? Okay, so, and the other part of your question, that is, if you have the true cost to go up to a constant, that is enough because it doesn't affect the optimal action. Yeah. Good, okay. So yeah, let's take the limit as everything goes to 0, okay? So let me make my notation super clear. I'll say this is what everything looks like when it's discrete. And over here, I'll do what everything looks like when it's continuous. So here I do states. S means that's a discrete set of states. Continuous states are X. My actions were A here. My actions are U here. You can do things in between, too. You can have, like, continuous state, discrete actions. Certainly, you can have continuous state and actions and discrete time. But I'll just, we're going to go all in one shebang here today. I try to use N for time over here and save T for the good stuff in continuous. Okay, so then my dynamics are Sn plus 1 f of Sn, An in this form. And since I'm going to go back and forth today, I don't want to have two different f's on the board that mean two different things. So I'm just going to scribble a little subscript d just to remind us that that's the discrete one. We're going to use both of them today, okay? But in general, I wouldn't write that unless I needed to name it for some other reason like that. And here, the dynamics are going to be f of x u like this. I'll write the t's explicitly for this time, okay? Here, I've got a sum. My long-term cost is the sum over n of some discrete additive cost. Not surprisingly, what I'll get over here is an integral over t. Oops. It can be, we're mostly talking about infinite sums and integrals so far. Now here's so up here we just said for all s, my optimality conditions look like this: min over a, L discrete SA plus J star F SA. And my policy is the argmin. That same thing. So the big question is, how does it work out over here? And I'll write it first, and we'll do an informal derivation in a minute. It looks a little funny at first glance, but it's beautiful. That's the form we're going to get, okay? And similarly, pi star of x is the argmin of the same thing. Okay, so we went from this equality here to something that's got a partial derivative in it, which maybe is not too surprising. We're taking some limits of these things. We're going to get a partial derivative here. This one is J of F of SA. So there's a nested thing here, which actually makes a lot of things gross. It really does. You have to evaluate your dynamics, shove that through your cost to go function. So even if your dynamics is beautiful, if J is a neural network or something, it's like any structure's gone, okay? This one, F stays nice alongside. If F is beautiful, you still have some hope for being beautiful for the whole thing. Okay? So I'm going to play with that and show you how, well, I mean, it's easy to see where it comes from in an informal sense. Hopefully the notation is clear enough. The other day I was working on a paper with some people, so a bunch of people, so it was like I couldn't just control the notation in the paper, right? And they had used X somewhere else, and I had to use S for a continuous state, and I was like, this is causing physical pain. I can't, I have principles, and I'm violating my principles. I really tried to be pretty consistent with that. Yeah. Yep. I think you'll see that real clearly right here, but it's basically, if you think about taking a Taylor approximation, the limiting case is like looking at the first order optimality conditions there. So if you take a Taylor approximation, you end up breaking that chain rule. Yes? I'm sorry? Over here? That's just 0. It's 0. My J on the left-hand side, poof, gone. It's one of the things that looks very different. You'll see why it disappears. But and it looks kind of like a weird thing, but you can still read this off. You say that this is a quantity one can compute. Its minimum value has to be exactly 0, and the U that minimizes it is the optimal policy. So it's still a well-structured equation. Yes? So here, this is just one state. It's not a trajectory. It's just one state. You could, if I were to evaluate this at S at a particular state at a particular time, I would write Sn, Sn is a state that takes a value at a particular at the nth step. This works for all S. I see. So the notation looks a little funny. Like, why did I write Sn here but only S here, right? And the reason is because those are different S's. That's the S at the nth step compared to the S at the n plus 1 step. Here, I just needed one S and one A throughout, right? And so that's, and it is true for all states, all times, for instance. Even in this one, you see, so I needed, because I've defined n here, I need to write S of n in parentheses to distinguish in the sum the different values that S is taking. But here I did not need to do that. It's cleaner to not do that. It works for all S. Okay, so let's just see the limiting, the simple derivation here, okay? You see why that 0 popped up. Let's do as if you're going to do numerical integration, an approximation using the continuous time dynamics that we could sort of simulate. How would you simulate, let's say, the continuous time dynamics? We could take our xn equation and we could do something like an Euler integration. This is just a first order approximation of the next step. This would be n plus 1 is equivalent to h seconds. This is my time step. Like the dt, t at time n minus t at n minus 1, something like that, yeah? Have you guys seen that kind of thing before, right? If I wanted to make an approximation of my continuous time derivative, or I want to integrate it approximately, yeah, then I get something like this. And similarly, I can say that my sort of discrete time version of my cost is like taking an integral over some time step of my continuous cost. Now, if I take these values and start popping them into the discrete cost to go equation, then I'll get something like this. So the changing from S to X, A to U, that was like just there was no mathematical change required in these equations. I could just choose to write a different variable letter here, but that now we have something that is a continuous state that I could take a derivative with respect to X or something, where I wouldn't have done that for S. Otherwise, this is just exactly the discrete equation with my approximation, h times LC is substituted here, and h times the derivative substituted there. Now, how am I going to approximate this j at x plus a little bit, right? I'm going to approximate this with approximately j star at x plus partial j partial x missed my h here. Right? Maybe I should even write that out more carefully, so that in general I could have a bigger derivative here. There could be other terms. You'll see forms of this equation that has, like, for instance, a partial j, partial t here. But our current formulation doesn't demand a time-dependent j, so I've left that out. Okay, but this is just what you would get from taking a Taylor expansion. Or generally, in our particular expansion, the only thing to expand is it's a function of x. J is always just a function of x. Okay, so, and by the way, this thing, even though I motivated it with just this approximation with the coarse h, if I take the limit, if I'm careful and take the limit precisely, that's where the details come in of analysis and the like. But if I take the limit precisely as h goes to 0, then that's going to be exact. Okay. Now here's the interesting thing. So if I just look at this, j of x here is inside the min over u, but it doesn't depend on u. So I can actually pull that out to the outside, and it cancels with this. So this actually, I should use my multicolor chalk to do that. So that cancels that term. And the strict dependence on j disappears, and that's how I got the 0 on this side. Okay. I still got this h hanging around, but I could actually pull this whole thing times h out, and it doesn't. In fact, it's getting in the way when I'm taking a limit as that goes to small, but that doesn't affect the min over u, doesn't affect the conditions. It should hold for any small h, so that the h can now disappear now that it's on every remaining term. And then I get to the original thing. Yeah? Evaluated at x, correct. I can be more specific about that, evaluated at x. I guess I didn't have enough notational power to do that better, but yeah. Was that your question? No. J is always a function of only state. It is implicitly a function of state because of u only because in order to compute the next x, so there's a chain rule here. So j of, I want you to see this as j star of xn plus 1, and xn plus 1 is x of n plus hfc x of n u. You see? So the j itself is only a function of a single argument, which is x. So the only thing I would take a direct derivative of is with respect to that argument x. And on the inside of that, I take the gradient of this thing with respect to, or well, I could take it, but I've just inserted this whole thing. Did I say that well enough? That's right. Yep. Yep. J star only takes a single argument. It's a function of a single argument. So the way that I'm going to approximate that is I'm going to evaluate it at a current operating point, which has got to be the current x. And I'll take a Taylor expansion, so I'll take a gradient of that plus the difference between this and the current one. So if I were to if I take any function f of x, and I want to approximate this with a Taylor approximation, I could say this is f of x at some nominal point plus grad f plus x minus x nominal, let's say. This is evaluated at x equals x nominal. That's what I'm doing. And it happens that the x that I'm picking here depended on u, but, sorry, this guy depended on u, but x nominal does not. Yeah. Yes?
So this is a
in the limit as h goes to 0, it's exact. Not the way I've written it. It requires a little bit more precision in what happens to functions as they take limits and stuff, but this gets you, that equation is exact. And this derivation is an informal way to see that exactly. So there are times where you get time dependence back in, but because in everything I've written, this is exact and there's no time dependence, no extra time dependence. So, so I only need to take a variation with respect to x here, and I'm evaluating it at a certain t, but if you saw that even this equation has no t in it explicitly, you can substitute any x and any u in, right? It's not looking along a trajectory of the system, it's a state value pair of the system. Okay, you just met a famous equation. This is a big part, that's called the Hamilton-Jacobi-Bellman equation. HJB. Okay, and we will refer to it often, the HJB. Yeah. Oh, sorry. Yep, it's the there are a whole class of PDEs is called the Hamilton-Jacobi equations. The ones associated with optimal control are the Hamilton-Jacobi-Bellman equations. And even this, if I were to change the cost function a little bit, you might get slightly different variations of it. But yeah, this is one instance of the HJB. Yes?
So the reason we wanted to write this equation is we wanted to actually find the K star, right?
Oh, it's better. It's better. You'll see. I promise. It's better. It's exposed. It's not hidden. Exposed. Okay, so let's actually unpack that equation just to get some intuition about it, okay? So remember our grid world example, right? Where I had the trash can robot moving left and right, and there's a goal, okay? Now I'm going to do like the infinitely fine grid world, okay? So still got a robot, still got a goal. Remember, I got, as I executed the value iteration, I solved for the cost to go, which was if I just had a distance sort of thing, I'd get these. I got a sort of a discretized version of my optimal cost to go, which is telling me the distance. If my cost was Euclidean distance, then it's actually going to be like Euclidean distance to that point. So these are level sets of the cost to go. So equals some constant. So maybe equals 1, equals 2, equals 3. Right? Those are the level sets of the cost to go. So let's unpack what we have here. So I want you to think about that partial derivative, that approximation, as, and this is kind of goes to your question about time here. So you can think about like how does J evolve in time, right? So J evolves in time like partial J partial X plus X dot, which is f of X U. How does the cost to go evolve if I were to follow a trajectory of the system? That's the term that we're thinking about. And what that equation says, what the HJB says, is for the optimal U, it must be true that dj dt, this thing, equals negative Lx u star. You see that? So this is dj dt. If I've taken the optimal u and gone and inserted it, then it has to equal 0. So just move it around to the other side. Move this around to the other side. It says dj dt is negative Lx u star. Okay, in words, what does that mean? That means if you're following the optimal policy and you're just watching your cost to go score, you got a little like indicator light for your cost to go score, your cost to go score is going to go down at the rate of your accruing cost. This is the sort of instantaneous running cost, right? This is the change in the cost to go. It says your cost to go as you execute the optimal policy should go down. And it goes down exactly at the rate that the cost tells you. In practice, dj dx looks, if you evaluate this at a certain point, dj dx is a gradient. I guess it's actually, this is dj dx, this is negative dj dx, yeah? So for u to be the thing that makes you go down in the cost to go, this is telling you exactly what we saw in the grid world, which your optimal action is the thing that wants to go downhill on the cost to go. And it's the gradient of that cost to go that tells you what direction to go in. The absolute value doesn't matter. The gradient, the truth was exposed, see? Okay, so this is sort of the heart, the Hamilton-Jacobi-Bellman equation is kind of the heart of the Hamilton-Jacobi, the HJB sufficiency theorem. So I named the equation here. There's also the HJB sufficiency theorem. As Jagdeep said, we ultimately want to use this to find the optimal controllers. But in the immediate, just like in the discrete time case, discrete everything case, we can already use this just to verify that you have an optimal controller. That's sort of step one. If someone comes to me and says, I've got an optimal controller for your problem, I say, prove it. The way they can prove it is by producing a J, producing the pi, and having it satisfy this condition and this condition. There's a few other boundary conditions and everything to make a complete sufficiency theorem, but these are the heart of it. And the boundary conditions are super technical, and like you can choose different ones, and this is the essential thing.
Sorry, this zero theorem is just if you find that u makes that equation 0.
And you have to give me the J. Like that's the hard part. Come up with a function J. Yeah. Yes. Good. So yeah, that's actually super interesting. So okay, so I wrote this. Nothing I said is inconsistent. So I said that J only depends on X, and the reason to make this a match, I had to not make it depend on U. It's only true at the optimal U, right? So everything I said is sort of still consistent with what you just said. We did observe in the grid world that there were multiple optimal actions. You could have gone, or like this. That actually does go away in the infinite grid world. The optimal action becomes to go straight there in that particular choice of cost function or whatever. But that's a little problem. I mean, maybe I think some things are more beautiful and continuous, but that's a little problem specific. You could still have non-unique policies in the continuous case. It just happens that in Euclidean costs, now there's a right answer to go beeline straight for the goal. The other thing, by the way, when you give me the j, you not have to give me a j. You have to give me a j that I can take a gradient of for all x. It has to be differentiable everywhere. That turns out to be annoying. Like even our bang bang optimal controller, the optimal j, we know actually, is not, it has a cusp. So partial j, partial x is not defined everywhere, which is why it's kind of hard to prove that that's optimal. Okay, but it does match these conditions everywhere, except for where the gradient is not defined. Okay, so let's exercise that a little bit. So I just said, if someone showed up claiming that they had an optimal controller, then how do you verify? Trust but verify. So let's do an example here. So I'll take my q double dot equals u system. I'll take as a cost function, x is q dot, right? So I'm going to do q squared plus q dot squared plus u squared. Okay. And since I'm penalizing u, and since it's going to keep my math easier, I'm going to just drop the u limit. So I dropped the for now. Okay, that's gone. But since I'm penalizing big U, I'm justifying that omission. Okay, and so here we go. I'm going to convince you that this is the optimal controller. Negative q minus square root of 3 q dot. Right? Someone shows up with and has a square root of 3 in their equation, you got to be like, prove it, right? All right, that looks a little funny. I'm going to need you to prove that. Unfortunately, my proof is going to also have a square root of 3 in it, but it's going to work. So there you go. I'm going to prove that by producing this cost to go function. I don't have to tell you where I got that. I will tell you later because I'm trying to educate. But I don't have to for you to believe that it's optimal, right? As long as it satisfies the conditions, you should be happy. Okay, and it turns out, so let's just think about the mechanics of this a little bit. So how do I write the conditions there? So I have 0 equals min over u of my loss function, q plus q dot squared plus u squared plus j, which is this thing here. But I need partial j, partial x. So let's just get the sizes of these things right. So x is this. So partial j, partial x. J is a scalar. X is a vector. So I want this thing to have two elements, which is partial j, partial q, and partial j, partial q dot. And then when I multiply that by partial j, partial x, f of x, u, right? This is a row vector. So that's going to work out to be a scalar as I wanted it to be. It's going to be partial j, partial q, partial j, partial q dot, the f1, which is q dot, and this one is u in my notation. Just to make sure, I mean, by convention, the gradient of a scalar with respect to a vector is going to go that way. Because you want to be able to take the gradient of a vector with respect to a vector, and you get a matrix, and things should multiply, and everything's good. Okay, so I can actually just write out this multiplication. I'm going to get this times this plus this times this. So I'm going to write that out as partial j partial q times q dot plus partial j q dot times u. That's it. And it turns out, so partial j, partial q, these are all a little bit of work, but easy. Partial j, partial q is going to give me 2 square root of 3q plus 2q dot. It's just taking the gradient of this. And I can take partial j, partial q dot. I can insert u into this equation. Okay, I can insert all those things in. And I promise you, I'm not going to do it on the board just because I'm running a little late, but all of those terms cancel out. Promise. It's just like all the terms just go, everything's gone, 0 for the optimal u. Okay? And so now, see, that's kind of somewhere between like I've solidly proven it to you to like kind of proved it to you and left it for as an exercise to the reader. Less satisfying, but I think probably the right decision for today. But maybe let's just think about how I take the min over u, because I need two things, right? I need to show that that's the optimal controller. I need to show that it is the u that minimizes that function. And I need to show that the minimum is 0. So how do I take the min of that? Okay. Well, what does that look like as a function of u? Right? It looks like u squared. That's going to be a parabola. And it's got a constant term. But the dominating thing here is that it's going to look like a parabola as a function of u. Those terms, that's like u squared plus partial j partial q dot u, right? Those terms that depend on u are going to form, they don't necessarily end at 0. That's not necessarily 0. I should make it more lopsided to make that clear. It could be something like this, okay? But for every q and q dot, if I just look at how it affects u, it looks like a parabola. So the minimizing u, since it's a positive, that's a positive upward pointing convex parabola, I can find the minimizing u by taking the gradient and looking at where it's 0. Okay, so I'm going to take the gradient with respect to u of that whole inside thing, q dot squared plus u squared plus partial j partial q dot plus partial j u dot u. The gradient with respect to u of that, I get 2u plus partial j partial q dot and that has to equal 0 at the minimum. The gradient equals 0. So I get that u equals -1/2 partial j partial q dot in this case. Partial j partial q dot, I should have just probably done it, is partial j partial q dot is 2q plus 2 square root of 3q dot. So I can just stick that in here, -1/2 2q plus 2 square root of 3 q dot. The 2's cancel. Ah, look at that. The optimal u. Okay, so that's just the mechanics of working with these things, right? So it's, this problem is not one that you should care about. It's just a kind of a simple way to see how we take those gradients and look for the stationary conditions and things like that. Okay, so let's draw that actually. So J, oh, go ahead. Yeah, this kind of looks like effort u squared, and this kind of looks like I want to penalize you from being away from the origin and having too large velocity. But this is, I would not give it a simple name. I'd give it it's a standard quadratic form for a cost that we use often, but it doesn't have an energy or position or whatever direct interpretation. So it's actually super convenient for all the math, so it shows up all the time, but it's a little weird in terms of normal units.
Does the J star have any movement?
It definitely does. Yeah.
And how do you come up
I promised I would tell you.
with it? Work backwards?
There are ways. There's a secret for making good homework problems, which is you can choose. So it's very hard. If I give you the dynamics and the cost function, it's very hard to come up with a cost to go function. But if I choose a cost to go function, I can come up with the dynamics for which that is optimal. It's a little trick if you ever need to write a problem set. So there's a couple little things like that. I didn't do that here. This one happens to be in the class that we know the solutions for in a general form. So this one I actually started with clean dynamics, clean cost, and that pops out. So I'm actually going to spend another minute and explain that. Both of those questions, I think, follow this. So let's just think about what what's happening here. So if I say in my phase portrait, my cost function, I guess red is cost, is like a quadratic form. If I just set u to 0, pick a particular value of u, the cost function is just trying to get me close to the origin, right, in the phase portrait. Just penalizing me for being away from there. That j that I got here, how does j look? J star of x, I could write that in a quadratic form. I could write that as x transpose square root of 3, 1 square root of 3, x. It's just the same way to write that, but in matrix form. And I could plot that, right? That's also a quadratic bowl, but it's an elongated quadratic bowl. It's not uniform anymore, right? If I take the eigenvalues and eigenvectors, I'll see that there's an eigenvector sort of along the line like this. There's an eigenvector in this direction. There's a bigger eigenvalue in this direction, and so you get this sort of like elongated. If I were to draw the contours of this thing, it looks like this. It's still quadratic, but it fell over this way and elongated. Okay, so just for context, remember when I did the value iteration example with the quadratic cost, spends all its time making the animation. Yeah. The cost to go looked like that. Okay. There's a little bit of a non-quadratic thing because of the boundary conditions in that numerical solution, but it gives, up to the boundary condition errors, it gives exactly this. Now remember our intuition there. Our intuition there was that this learned something about the dynamics, right? What is it saying here? It's saying if you're over in this quadrant, you're at a lower cost than you're at a similar place in this quadrant. Why? Because you got a positive velocity. You're already moving towards the goal. But if I'm similarly far away here and I'm moving that way, that's worse. That's a worse place to be than here. It understood the long-term dynamics and stretched it out exactly to capture that. Okay, cool. Yeah, it turns out if you did the minimum time version, you can, again, apart from the fact that the gradient disappears at the cusp of that, it does satisfy the conditions everywhere the gradient is defined. So it's like mounting evidence that that was an optimal policy, but I didn't actually prove it yet. Okay, where did I get this? I promised I would tell you where I got it. Where did I get it? This is actually just an instance of one of the most famous optimal control problems ever, which is LQR, linear quadratic regulator. I hid it behind the square root of 3, but there it is. Okay. So what's the general form of this? This is called the linear quadratic regulator. Okay, so in general, if I have a continuous time linear system in matrix state space form, and I have a cost function that in the general form is, actually I keep that off. Okay. I'd like Q to be positive or semi-definite. Okay, I'm going to tell you what that means in a second. Right, so this means it's a positive semi-definite matrix. This means it's positive definite matrix. By convention, that also means that they're symmetric. If you say something's a positive definite matrix, that implies it's a symmetric matrix. Okay, so this is a pretty general quadratic form. Then I can tell you that for any problem like this, we can find the optimal solution for the infinite horizon cost. So infinite horizon. And it turns out the cost to go function is a quadratic form. So I got just in my picture I just erased, but I got a quadratic cost, and then I got a quadratic cost to go. They were different functions. The cost to go captured the essence of the dynamics. The cost didn't. The cost was instantaneous. The cost to go is long term. Okay, but in these linear problems, they stay quadratic. Okay, so if I just only assume for now that there's this form, then I can go through the math, and you can see that we can always find a solution in this form. And again, that should convince you, because all I need to do is produce a solution, right? If you want, again, we're going to like turtles all the way down here, but if you ask me where did you get that, I can tell you the answer to that too. But that's like linear systems have quadratic storage functions. I wrote a little bit about that in the notes too, but yes. Mm-hmm. I'm going to choose how to accumulate cost. I'm going to say, I'm going to take the integral of this from 0 to infinity. That's the horizon up here. If I were to make this 10, then the equations are mostly the same, but they become time dependent. So it gets a little bit more complicated. There's like artifacts from being close to the end of time, right? If you know the bank's closing it, no one goes to banks anymore. If you knew like, it's like online banking's open all the time, that's a bad analogy. What closes? Like pizza or something closes, you know, cafeteria closes at 5 or something, and it's 4:50, you might act very differently than if it's 3 o'clock, right? So there's boundary effects as soon as you have a horizon in time. Infinite time tends to be cleaner as long as your integrals converge. And whenever you write an infinite there, you just have to make sure that you can get to the cafeteria. Because if you can't get there and you accrue some small cost infinitely far into the future, then it's going to blow up. Okay, so I can turn the crank here. I can do exactly the same sort of thing. I can say what's partial j partial x. You gotta kind of have to practice taking matrix derivatives, but it looks like that. Okay, it's maybe not surprising, but it just getting your, you know, it's going to have to be a row vector, and that, okay, that's a row vector. That's good. You know, it should probably have a 2 because things squared, you're going to have a 2 in front. You know, and that's what it works out to be. Okay. And you can now plug that into our cost to go. Min over u, x transpose qx plus u transpose ru plus partial j partial x times ax plus bu. And we can do the same kind of machinery, but just in vector form that we did in the specific case above. And it turns out we can solve exactly for the optimal u and the optimal s as a function of q, r, a, and b. Okay. If I take the gradient of this thing, can I just write gradient of that thing on the inside here with respect to u? And I set that equal to 0. Why? Because that's still a quadratic form in u. And I restricted r to be positive so that quadratic form was going up and it has a unique minimum. I also don't want it to be optimal to take infinitely large actions. So it's good to be positive costs for bigger actions. Okay. If I take the gradient with respect to u, that gives me the optimal controller. That tells me that u star is negative r inverse b transpose sx. Just exactly what we did above. That's what pops out. And that looks like a lot of symbols, okay, but it's all linear. So it's just the optimal controller is a linear controller. We almost always call it k. Yeah? And we always keep the negative around just because you know, we learned a long time ago to be afraid of positive feedback. So it's just like let's remind ourselves that it's not going to blow up by keeping that negative outside. Yeah. Zero. It would require your dynamics in Q to be consistent with that. There are problems for which if you have no costs along that axis, right, and no dynamic, I mean, maybe if I just had a trivial dynamics that had x dot equals 0 in one axis and cost equals 0 along that axis, it could still go through the equations, but it would have no preference on where it was in that direction. So S would be a trough. Yeah. Yep. So it feels like it should be restrictive, but it's actually very general, right? Everything in RL is this way, right? It does sometimes, you play games and you put weird cost functions in to catch your long-term dynamics. The things that I, in my life, have found, like, I kind of wish you'd done stick it in, and you have to do a little, you can stick it in, almost anything, but for instance, if you want to say, like, the difference in actions is small, right? Say that I don't want my actuator to change rate or change command too fast. Then you just have to augment your state space so that your previous U is one of your states, and then you can write that cost function. So there's almost always tricks you can play like that. But this additive structure is essential for Riccati equations and for the Bellman equations to have that form. Yep. And then similarly, if I were to stick this U back in here, I get another famous equation, which is, sorry, I just used the word Riccati equation, but I had not introduced a Riccati equation yet. Here's the Riccati equation that I just lovingly mentioned. If I put this back in and I cancel out all the terms, you get this function that looks like this. Q minus S B R inverse B transpose S plus A transpose SX plus SA equals 0. So, it's interesting that the optimal policy, even though it's a linear function, it's a function that includes S. You have to know S, the cost to go, in order to know the optimal action, right? That's not surprising. To get the optimal cost to go, you have to solve this matrix equation. Okay, so that, since I kind of skipped a step there, you get a bunch of things that look like this. If I collect all of the terms that are quadratic, and those all have to equal 0, that would be the first thing. This thing would be on the inside. If I just gather the terms, make them all a function of x. And since that equality has to hold for all x, then you can actually remove the scalar equation and say all elements of that matrix must actually be 0. Right, so this thing here that has to be 0 is a scalar. But since it's a quadratic function of x, and it has to hold for all x, every element of the matrix has to be 0. Yeah? Yes, that's why we make U positive. Positive, strictly positive, semi-definite. Positive definite, strictly positive definite. It's exactly precisely because we want to be able to take that R inverse. Okay, so if you look back at your matrix calculus stuff or something, matrix algebra, how do you solve that for S? It's actually quadratic in S. It's an ugly thing, okay, but it was so important that we found out really good numerical recipes for solving that. Okay, this is a Riccati equation. Did I just do what I teased Max for doing? I think I did, didn't I? Is it once you? Now I confuse myself. I didn't write it anywhere. It's got to be. I think it's 2 C's, 1 T. Riccati equation. Yeah. Okay. So in practice, you can just, I'll show you. You can ask MATLAB or Drake or other, controls packages. You can basically just say, I have A, B, Q, and R. Call the linear quadratic regulator. It will give you K and S. Right? That's become a numerical recipe that's just extremely good. Okay, and guess what? If you call it with those matrices, you get square root of 3 out, which is where that's the truth of how I did that. and well, it was like 0.33333. I was like, okay, or whatever. It was the square root of 3, and I did some rounding, verified the equations, made my example. Okay, so let's just think about this in parts a little bit. That looks a little mysterious at first, but I want you to understand it. So I have a cost to go function. Okay. These are my level sets. This is like j star of x equals, a constant 3, 2. The first thing I want to think is, what's partial j partial x? That tells me what direction I want to go downhill, right? Ultimately, we want to go sort of negative partial j partial x, right? So partial j partial x, we said, was 2x transpose sx. So negative of this, I'll put a negative on both sides. My negative sx term, that's trying to go downhill. So if I break this controller apart, thinking from here, I'm going to try to go downhill. Okay, but I can't go arbitrary directions. I don't get to pick any u because I'm underactuated. So I have to modulate my expectations about going straight downhill by what I'm capable of doing, which is the B matrix. Okay, and then R says some actions cost more or less than others. So again, it can skew what's the fastest path you want to take down the landscape. But really, I want you to think about this as a small modification on partial j partial x, going downhill. Yeah? Roughly trying to go down. So LQR is going to be a workhorse for, you can take a lot of interesting, complicated systems. You can make a linear approximation for them. And it's really amazing that for any A, B, Q, and R, positive Q and R, it will give you a stabilizing controller, like for very complicated systems. Okay, so that's even if that's if the linearization is limiting ultimately, maybe you need to take the nonlinear dynamics into account. It's an excellent sort of starting point for a lot of control. You can sort of at least get something that doesn't fall down, and then try to improve from there. So as just a kind of a fun example. This was my robot that did fall down at the DARPA Robotics Challenge, our copy of the Boston Dynamics robot, early one, right? This is just a simple, quickly coded up thing where I put a pin joint between the toe and the ground, because there's a contact and no contact problem that we're going to study later. I didn't want to solve that in this particular example. I picked a nominal configuration for Atlas. Okay, and I said, here's a cost function that says try to be close to that, but using, and minimize action. And it just does this. It balances. It's balancing Atlas on a toe. That's a lot of dimensionality, a lot of degrees of freedom. Super fast solve. Like we can solve that for big X and U. Okay, big A and B matrices, and that's going to work for even very complicated systems as long as they're smooth. Okay, so we'll come back to that and build on that later. But that's one of the most famous results from continuous optimal control. Good. I'll stop there. Yeah.